Hello students, today's discussion will be diversity concept over the feeding channels. In the last module we have learned about how wireless communication is about, what is the meaning of feeding in the wireless channel, what are the different kinds of the feeding that we deal with in a practical system design, and we have seen based on the RMS delay spread of the channel and the coherence time, coherence bandwidth. We can have the 4 different combination of the channel situation, namely frequency selective flat, frequency selective frequency selective slow, frequency selective fast fading, flat slow fading or flat fast fading channels. And also we understood that once the signal is released from the transmitting antenna, it never reaches to the receiver via a single path, rather it reaches over the multiple paths after getting reflected and scattered by the different scattering objects and elements of the wireless environment, and that complete phenomena is called the multipath propagation of a signal. Today we will try to learn what is the meaning of diversity over this multipath channel propagation. So, it is a situation where we can, is there any gain of this multiple path reception of a same signal in a receiver front end? Can we get a gain out of it, or it is totally a loss always? Already we have seen in the last module that because of this multiple path propagation, signal gets dispersed. The bandwidth gets dispersed, and over the time axis it is getting dispersed, over the frequency it is getting dispersed. Because of the dispersion, maybe lot of the signal processing we need to do in the receiver, that is easily understandable, but can we get any gain out of this multipath propagation? Today we will try to learn that. So, what is the diversity? Diversity schemes they refer to a method for improving the reliability of the message that we are receiving, and if we can improve the reliability of this message by using 2 or more communication channels. And remember, all those communication channels needs to be different with characteristics. They need to be completely independent with each other. It is something like that. If I am giving you the multiple channels, or say multiple pipes, and if you are about to send the same message signal, and if you replicate the same signal over the multiple paths, and here if you, and all the paths are actually independent to each other and having no correlation with each other, hence there is no interference actually, and if you receive this replica of the same signal independently in a receiver, so by combining them in some way you can get a huge gain over the noise. The signal power can be boosted up several times over the noise as well as over the in presence of the interference also. So, this is the fundamental concept of the diversity. So, you use a multiple represent a replica of the same signal over the multiple channels, or by some means of the way you multiply it and receive it over the different way, and combine it in such a way that reliability of the message can be improved if I can improve the received signal to noise ratio. So, diversity actually here can be done over the several means. We will discuss little bit later, but if it is done for doing it for through the channel, we need to have the uncorrelated paths or uncorrelated channel that I have explained here. This uncorrelated channels I have drawn here into at least I have considered 2 different channels here, where the channel properties are actually different over the different portion over the different if I move along the time axis, and this channel condition is such that the channel number 1, it is a blue line, he is having some deep fade, that means the amplitude is getting heavily down, and it is totally it will be down actually for this time periods. Time axis this, time axis over the time instant this, over time instant this, and over the time instant this for the over the time instant this. So these are the conditions, say actually for the blue one, the time instance 1, the time instance 2, and the time instance 3, the amplitude will be heavily down of the transmitted signal. For the channel number, if it is a channel number 1, for the red channel, the amplitude will be heavily down for the channel instance say 1 dashed, and then the channel instant 2 dashed. So remember one thing, the wireless channel, if they are multipath channels, I mean to say, if they are uncorrelated, it is highly impossible that both the channels will give you this exactly same kind of the profile over the same time domain, at the same time domain. And so at a particular instant, if you check the condition, if you check the profile of the two different paths, one path you may see actually heavy fade channel, heavy deep condition, but another channel there won't be a that much deep situation. So if I combine the received signal of these two instants at a particular instant from these two different channel, so by combining the effect proper way, I can receive my signal properly. Whereas if I use only the blue channel at this instant 1, my signal, received signal power will be heavily down, and I may not be able to detect the signal also. But if I take the combination of the channel 1 of the blue and as well as the red channels, there is a high chance that I can actually discard one reading and I can take the other reading, or I can take the average of these two reading, and actually I will get a very pretty good amount of the received signal power over the noise, and which will help me to properly detect the message. So that's the way actually we that's the meaning of the diversity that we are trying to bring here. And remember one thing, on the left side I have drawn a channel that two certain multipaths over a certain instant of the time, it's such that they are heavily correlated. So their profiles are actually correlated in the means the change of their amplitude and the phase profile of both the channels are going hand in hand almost. So there is not much difference. So in such a cases, whatever the effect the signal will experience in the blue channel, he will experience the same kind of the fading path in the red channel, and hence there is not much diversity gain possible if I combine, if we choose these two channels for the transmission for diversity. So channel to get the diversity effect or diversity gain, the fundamental point is that you have to have some differences between the two paths, and they should be uncorrelated. That's why we say they are uncorrelated. Here correlation between the two channels are very high, and here the correlation is almost 0 kind of. So more the correlation is less, more you will get the gain for the diversity combining. So all these independent paths will be combined in such way in the receiver. Remember, there are several ways of combining the signal received over the multiple paths that we will discuss later on. So the types of the diversity techniques, let us quickly revisit. Based on the type of the fading, we have two different kind of the diversity. One is the macro diversity as well as, and second one is the micro diversity. The macro diversity technique is to mitigate the shadowing effects that is a very common situation happens when outdoor communication goes on, and it is an effect coming from the buildings and different objects. So to avoid the fading that is happening because of the shadowing from the buildings and the objects in a wireless environment, we go ahead with the macro diversity technique. There is another thing which is called micro diversity, which is essential to avoid or to mitigate the effect of the multi-path fading. And most of our schemes that I will discuss here is about the micro diversity, and based on the location also there may be two different kind of the diversity. One is the transmitter diversity, another is the receiver diversity. So diversity is employed at the transmitter, I mean the transmit maximal ratio combining schemes and all, they are going ahead, or you are doing the diversity combination in the receiver where you are providing the diversity effect, where you are actually employing the gain, and the gain will be wherever you are where actually the diversity effects is employed. Based on that either in the transmitter side or in the receiver side. We call it a transmit diversity or receive diversity. The example of a good example of the receiver diversity is the maximal ratio combining or selection combining or equal power gain combination, all that. Based on the resources, diversity classification will be like this. Number 1 is time diversity. What you are doing in time diversity? In time diversity, the same signal you have certain time for transmission. You can divide that time over the smaller epoch, and this over the small epoch you are repeating that signal over the each and every timing epoch. So, the signal that you are transmitted here they are basically same, but you are repeating the same signal over the multiple time intervals. How do you feel that it will give you a gain? It will give you a gain because we understood already that the channel condition never remains same for an wireless environment. So, it is expected that even if the channel here is in the fast time duration or maybe fast 3 time duration, channel condition is extremely bad. Bad in the sense actually means the fading effect, very deep fades are happening. So, I am not going to expect actually very good signal in the receiver front end, but after some time there is a chance that the channel condition or the fading situation will change in the time duration 4th and 5th, and then you will get a very good signal power, receive signal power will improve. So, this is called time diversity, where the same signal is transmitted over the multiple time intervals. Frequency diversity, and finally, the decision over the time diversity channel will be going on by taking an average over all the time epochs, maybe, or best out of all that, or maybe a combination of the base 2 or base 3, maybe any logic you can apply in the receiver. Frequency diversity case, what we do, we have a given bandwidth for transmission. We will actually divide that bandwidth over the small chunk of the frequencies, and we will keep on resending the signal over the same signal over the multiple frequencies. So, it is something like that, your signal is repeated over the multiple frequency bands. So, this is a frequency over the frequency axis wise, you are having the diversity, and by combining the signal over the multiple frequency bands in the receiver, you can have a narrow band filters, and you can filter out and you can detect the signal over every frequency bands, and finally at the output of the detectors you can combine them by the best possible way you think is possible. So, in this situation also again the consideration is that the condition may be very bad over any part of the frequency. So, some part of the frequency band the channel is behaving heavily badly, but fade is very high, but for the other frequency bands actually there won't be a condition. This situation is very good actually to avoid the interference also, because interferers are the narrow band interferers. Sometimes they present in any one of the narrow band, and even if actually your signal is getting heavily affected because of the presence of interference, maybe in one of the frequency bands, you will be get rid of them if you combine the portions of the other frequency bands. So, frequency diversity can give you an inherent resilience against the interference also. The third one is the space diversity. We use the multiple antennas which are spaced apart, okay, and we transmit the same signal from the multiple antennas in the transmitter side, and the way it traverses via the multiple paths and reaches and it is reached to the receiver front end, and we combine them at different logic. So, it is the space diversity that you are getting. This is the time, this is the frequency, and this is the space. We can also have the angle diversity. So, we can restrict the receiving antenna beam width to a certain way, that this is actually heavily focused maybe towards this antenna sometime, then it may be focused on this, and this may be focused on this. So, it is you are restricting the you are zooming basically a certain portion of the part, and you are receiving actually the energy over the small selected zone of the angle in the receiver section. So, we call it the angle diversity, as the angles are different from in these 3 beam patterns. So, you can actually get rid of the interference also if the interference is coming from this angle or from this angle. So, it is an angular basis filtration you are doing, and you can go ahead with the combination of this filtered outputs in a best possible way you feel actually good for the signal detection. The fifth one is the polarization diversity. Using the antennas with the different polarization, either vertically polarized or the horizontal polarized or circularly symmetric one, you can go ahead with the different diversity over the polarization axis. But remember, the more time frequency are the easiest one to go ahead with, and space polarization, angle diversity, they demand the complicated transmitter receiver architecture. In the space diversity, we implement the multiple transmit or the receiving antennas. We call them the antenna array. I draw it in the last slide, where these elements and the arrays will be separated by a distance. The coherent combination of all these array elements, the signal received from these array elements, we will be actually help us to increase the signal to noise ratio compared to reception via a single receive antenna. So, this is basically this diversity or the transmit or the receiving side. We prefer to have both way if you wish to get the maximum receiving space diversity, and this enhancement on the signal to noise ratio is largely dependent upon the number of the antenna array elements involved inside the process, we at a cost of large hardware complexity. And this space diversity also requires that the separation between these two antennas must be such that the fading amplitudes corresponding to these paths are approximately independent. So, you cannot bring both of them too close such that the paths, the correlation the paths to paths associated to these antenna elements are becoming correlated. Once it becomes correlated, then the fundamental actually gain of the diversity will be heavily damaged, because total gain of the diversity relies on the fact that you have to keep the uncorrelation of the different paths. You have to ensure that, and to ensure that, we have to maintain certain distance between these antenna elements in the antenna array. Usually, we have seen that half of the wavelength, one half of the wavelength, or approximately 0.38 lambda, exactly to be specifically to be said, it is actually a good difference between the antenna elements to go ahead with the independent fading over the multiple channels when the space diversity is deployed. This slide is talking about an example of a receiver diversity. What is going on here is your receiver front end is now having an array of the antenna elements, and now you are thinking that each and every antenna, the distance between the elements are such that they are capable to capture the signals who are uncorrelated to each other. The channels that are associated to each of the antenna elements are uncorrelated. Hence, we expect that the signals received by the array elements, they are uncorrelated to each other. In the receiver diversity, to achieve the diversity, we actually, the output of each and every antenna element, we adjust them by some gain factors, and finally, we add them up and combine them up. So, the SNR actually it is expected to see that this addition will be co-phased addition if we can align the phase of each of them, if we consider that they are well phase aligned, all the elements are. So, then actually the output will give you the maximum SNR, and you can feed this output to a detector to detect the message signal. Remember, actually we call it if I am having capital M number of the antenna elements, so varying from 1 to capital M, here we will call it a M branch diversity in the receiver. And once we are receiving these signals, the SNR of each and every path, if they are co-phased, well phase aligned, I mean to say, then the SNR of each and every path will be given by the Ri square by Ni. I is the number of the path, R is the received signal power of that path. So, Ri square will give you the signal power received in that path. And if I consider that the noise bandwidth also over all of them are exactly same, and the power spectral density of the noise, they are also same, and they are the additive wide Gaussian noise I am considering for this analysis, then finally the noise component, the SNR values for each and every path that is associated here will be same and will be governed by the Ri square by Ni. So, most of these combination techniques, if you look into this combiner, they are basically the linear, and this output of this combiner is just will be the weighted sum of all these fading paths or the branches, and this M order diversity will be very easy to get at the output. So, with this example, so let us quickly look into the facts when one or when more than one of these weight vectors they are non-zero, the combiner adds together the multiple paths. If all are zeros and you are having a single path value of alpha equal to 1, then this is a single path communication. It may be a line of sight path only you are receiving. Otherwise, actually if the alphas are non-zero, then you are going to combine the weighted sum of each of the paths or the multiple paths. So, once we consider that the signal are co-phased, and where the phase theta I of the ith branch is called as theta I is a phase of the ith branch associated to it. So, then the phase theta I of the ith branch can be removed through the multiplication by this, and hence we remember, hence we say that alpha I is equal to the a I of e to the power j theta I for some real value of this a I. Once actually this phase removal is done, and this phase removal definitely demands a coherent detection of the each branch's phase properly, and let us assume that it is properly detected and it is removed accordingly. So, the coherent combination of this independent fading paths is possible to mitigate the effect of the fading over the paths. And what we will be ending up with in a co-phased such kind of the co-phased situation and the removal of the phase information from the received signal over the multiple path is that if I am transmitting the signal original signal ST, and if it is multiplied by the random complex amplitude term, so the over all the path the total complex amplitude term will be given by AI into Ri. The summation is running over all the total number of the multipaths. Multipath I is denoting the number of the multipath. This complex amplitude term results in a random signal to noise ratio definitely, and at the combiner output, which we should have some probability density function. Here we are writing that probability density function of the SNR, the summed up SNR as P gamma sigma gamma. Next, we understood that there are two different types of the performance gain associated with this concept of the diversity. One is the receiver space diversity mainly, one is the array gain, another is the diversity gain. So, let us first look into the gain that we are getting from the diversity, and let we are having Ri, the received signal is equal to the square root of this Es. Es is the symbol energy. Let us also assume that there are the identical noise power spectral density over the each and every branch, and we have used the pulse shaping in such a way that B into Ts is equal to 1, the bandwidth time bandwidth product of that design is equal to 1, and such that the every SNR each and every branch of every branch can be now talked about by Es by N naught, and let the AI is nothing but the Ri divided by square root of this power spectral density N0. Then this summation of this SNR is basically will be given by the power of the received signal AI into Ri, that summed over all the paths squared up, and here also this is the divide, which is a normalized factor by AI square, and then this is a noise power. And then finally, if I am doing some calculation, we will be ending up with M into S by N0. And remember here that if the signals are coherently added, if they are co-phased and they are coherently added, then only in the presence of the noise, in absence of the interference, we can have the received signal to noise ratio, I mean additive signal to noise ratio is m times higher than the case of the conventional receiver, where the diversity is not deployed. Remember, this capital M is given by the number of the antenna array elements deployed for this or involved in this combination process, diversity combining process. And if we go further, for this situation we can compute the outage probability and the symbol error average symbol error probability by these two equations, where this Ps gamma is the probability of the symbol error for demodulation of the signal over an AWGN channel, and this one is, we understand, we described in the last slide. It is the probability of getting this additive sigma SNR, additive SNR, and outage probability is given by this expression, where the gamma 0 is a selected threshold value. We will describe here at least one of the diversity combination scheme, which is the maximal ratio combining, the mostly used technique in the practice. In MRC, the output is weighted sum of all the branches. So, in this figure 2 that we have seen, here the MRC will be the weighted sum of all their branches at the output. So, the way we will write is like this. So, since the signals are cophased, I understand that this is possible, and then the output of the combiner will be given by I into Ri, where I is moving from I to M, and we assume that the power spectral density in each and every branch is same, and hence the total noise power, combined output for the noise power, will be given by I square into N0, because I is getting activated over the signal as well as the noise. And now the signal to noise ratio at the output of the combiner will be nothing but the R square by the total, and here we are ending up with this whole factor. So, now what is the goal of this maximum ratio combining is that you will try to choose the AIs in such a fashion that it maximizes the signal to noise ratio, this gamma, sum of the gamma. So, intuitively the branches who are having the high SNR values, we will try to give the weightage higher, we will try to choose a higher weightage factor there compared to the branches where the low SNR values are there. So, it is something like that. We will compute the SNR values of each and every branch of the received paths, and you choose the alpha i's in such a way that wherever the SNR is high, wherever the SNR is maximum, you give the value of alpha also maximum there, and the values where the SNR is a lower one, you choose the alpha value also minimum. So, we do not put the weight or adjusting the weights as in such a way that giving the maximum weightage to the higher SNR paths, our total sum up, the summation will be very, very high. So, target is to maximum this by choosing this value of the AI in such a way that it is performed, and this once we are doing this SNR, we are maximizing the SNR, finally the gain will be over the detection process. So, optimal weights now that we have selected is given by this, I understand. Resulting combiner has come like this. And so, if I try to see what is the distribution of this summed up weighted SNR values, summed up portion is coming up. We take the product of this exponential moment generating or the characteristic functions. If you consider that the Freding is a Rayleigh Freding on each branch, and the equal average branch SNR is equal to gamma, and then the distribution of this additive function, this sum of this SNR values will be chi-square distributed with 2 m degrees of freedom, and its mean value will be given by m of gamma bar, and its variance will be given by this. So, this chi-square distribution is invoked here. The corresponding outage probability, which is nothing but the integration of this distribution function over an interval of 0 to the selected choice of this gamma value or the threshold value, will lead you to this exponential distributions. And if I try to plot this values of this outage, we will be able to see that if I am increasing the number of the diversity, the outage probability is improved, and we are getting actually over the normalized value of this gamma with respect to the threshold. If I try to plot on the x axis, so with the increase of this diversity, we are outage actually improves. If I now try to check what will be the error probability calculation, if I taking an example of the BPSK over the independent and identically distributed Rayleigh fading channel. So it will be the average error probability will be given by the Q function, we understand, and given Q function is actually it's variable with the parameter gamma on it, and it is now getting affected will be by the distribution of this sum SNR, and finally it will be, if we solve it, it will be given by this expression, where this capital gamma is nothing but given by the average value of the SNR. Now, in order to solve this expression, we take a example upper bound on this average probability by applying the Chernoff bound on this Q function given by this Qx less than equal to the power minus x square by 2, and therefore, the symbol probability will with this structure of this capital M number of the branches, as we have shown in this figure, will come down to the formula here. And if I actually integrate this integrate this part over the chi-square distribution over all the branches of capital M, then we will be ending up with this. So, this final equation of 1.10 simply says that at a higher values of the SNR, the diversity order of this MRC, the higher values of the SNR at high value of this gamma bar, the diversity of order of this capital M is the diversity of the MRC is capital M, and so MRC achieves a MRC can achieve the full diversity order itself. So, symbol error rate will be heavily improved if I am keeping on increasing the diversity order. So, you need not to increase the both. So, but if the SNR value is high only, you can have the high order of the diversity effect, and the gain from the diversity is easily visible for your MRC. And this is a very simple example, the way we do the diversity combining in the receiver. There are several other processes, for example, equal gain combination, and if you are interested, you can refer all those different diversity techniques from the standard wireless communication book by Rappaport or wireless communication by Andrea Goldsmith, and we will actually apply any mostly by MRC combination in the further related to our kind of the discussion in the spread spectrum communication. So, I have explained the MRC mainly in this module.